Hey, hello guys. Good morning. Uh, so we have been discussing the problems on cache coherence. So the last two session we have been discussing about the problems on snooping based protocol. So now, right, we will move on to directory based protocols. So we have seen already, right, we have like two different type of memory architectures. One is a centralized shared memory, and one is the distributed shared memory. For centralized, we have seen the snooping, and for distributed, we have gone for directory based. So similar to snooping, here also we'll see when any operation happens, how the request, I mean, based upon the request, how the memory and the caches is going to get changed. So as I told you, this is the distributed shared memory architecture. So let it be, we take as an example here that we have two chips, each is having these four processors, and it is shared, and each will have its own memory. So each individual processor will have its own cache. So here, right, we have an L1. I mean, every processor will have its L1 cache and L2 is shared. Similar cases here in case of chip. So suppose if P0 is requesting for any, whether it is a read or write request, first it will check whether the data is available in L1. If it is not, then it will go to L2. If it is not, it will check whether it is satisfied by chip on L2. If not, right, then only right the request will go to the memory. Okay, so this is the way. So L1, P0 to L1, after that, then to L2, and then to this one, and finally, as depends upon the address, it may goes either to M0 or to M1 because we know, though it is a shared, distributed share memory architecture, the address will be like this. Say, for example, 1 to 10 will be in M0. So 11 to 20 will be in M1. So it will be like this only. So based upon the request, the data will goes to that memory. Because we have seen, right, when the request is when the request is satisfied by the cache, probably right the number of stalls will be much lesser compared to the memory. Okay, so first it will check all the caches, then only right it will goes to the memory piece. And when you just look onto this table, here right we have something called this directory because it is a directory based protocol. So obviously we have here M says that it is modified, shared, and invalid. We have these three. We have seen right three stage. And I explained the directory based protocol. I hope you have seen. So three state. And a few more notations you have to be careful. Here it is saying this C0, C1, C0. So what it says is right, this address block is shared by this chip C0. 108 is if it is shared by both the C0 and C1. So that's what it is conveying. And here one more case is here. What it says is 108 is shared by P0, 0 and it is externally used by some other chip also. This E says that externally. So externally some other processor is also using. Because L2 will contain the information about the processor belongs to chip 0 only. Okay. So, but it says that it is externally used. Because if you take a same case, see, 108, P3, 1 is using externally some other processor is using. That's what it is conveying here. So, um, so this is the base idea. So now, right, as we discussed with the snooping cache coherence protocol, here also I'm going to give some set of operations. See, listen carefully. The questions will be very clear. Um, Sometimes there may be a dependence between the what to say operations, or it won't be. If it has been given like A, B, C, so there is no dependence. So you can do like this. Suppose in a B, if you have three operations, we have to, so there is a dependence. So accordingly, right, we have to update the directories or memory cache, whatever it is. Okay. So I will try to solve both the problems. So I think this is what for snooping also. Read carefully. So if the operation has been done sequentially, accordingly you have to update the tables. Okay. Or else if they gave only one instruction, then no problem. And there won't be a dependence between like A and B. Say suppose if we have like this, for example, okay, say A something, let it be read, P naught, comma 0 is reading B, P naught, comma 1 is reading some location 100. So here there is no dependent. Okay. So whatever after this, whatever the things you have to update this. After this, whatever the things you have to update. Sometimes right may have like this P naught comma 1 write operation, P1 comma 0 read operation. So this is sequential. Okay. So after doing this, what will be the state? So that's what we are expecting. Okay, so this one there is no dependence between this and this, but within this sequentially you have to execute, and whatever the final state you have to display. So it is applicable for both snooping and for directory based protocol. So first we'll see some 2 to 3 examples with respect to directory based protocol. The same scenario. Sorry. We have this. Suppose this what it is P naught comma 0. It's performing so this is performing the read operation to the location 100. So it has been given as P naught comma 0. So what we can do, just go for P naught comma 0. So as I told you, first it has to check its cache, L1 cache. So this is the L1 cache. See, in this scenario, L1 it's stored 2 blocks, L2 is storing 4 blocks. And here also, right, everywhere 4 blocks. So what, you know it, right? Suppose if this is B0 and B1, suppose this block 130 has to come, where it has to come? It has to come to B0. And this has to come to B1. Okay. So I think morning I explained with respect to snooping. So the same thing here. Here, because L2 is capable to store 4 words, but L1 is capable to store 2 words only. Okay. Sorry. So now, right, P naught read 100. So first P naught will check its L1 cache. When it check L1 cache, clearly the data is 100 is here, and it is in modified state, which means this is having the exclusive. So it is going to be a read hit. So no changes, nothing has to be done. Directly the data will be read. So no other changes. Okay. So it is as it is. Next, right, we'll go for the other things. We take this P naught comma 0, so which is reading the address 120. So 128. This is the book path problem. Just I'm trying to solve that. So when it is 128, we just check. So similar. Sorry. $128 is not available in L1 cache. So here, right, you will have a miss. Let it be in C naught, P naught comma 0. We have an L1. We will have L1 miss. So there is no data. And then, right, it will check L2. So L2 also it will check. In L2 also we have only 108 because we clearly know 128 means it will goes to block 1. So here also, right, the block 1 is having some other data. So in L2 also we will have a catch miss. Okay. In chip 0, both L1 and L2 is having the data catch miss. So now what has to be done? We need to check the L2 of these processors. Okay, so we will take only as 2 chip. Currently this will take like this, and this is a 0,001. This will make it as 1,3. Yes, we have taken only 2 chip. So when it is 2 chip, right, this is going to be chip 1 processor 3. We'll take like this. Okay, chip 1 processor 3. We'll take like this. So when you go with L2, this L2 also we don't have the data. 128 is not here. So probably right in C1 also. So we have in L2 you have a catch miss. So what has to be done? So probably right we have to move on to the memory. So the data has to be read from the memory. So when you just go with the memory, so it is invalid. Invalid in the sense the data is not cached by anywhere. That's the meaning here. It is uncached. So now we need to cache it. So when you're doing it, first what has to be done is right, the data has to be written to L2 cache. First it has to return to the L2 cache, and from there it has to return to the L1 cache. Okay, no need to write it here. Only here you have to write it. So the changes I'm putting in the block case. So I will change the color. So if you take P0, 0, that is chip 0. In chip 0, L1 cache, block 1, right? Block 1 is going to be a shared state, and it is going to read 128, and the data is 0028. So this is for L1. L1 block 1. And if you take L2, in L2 also, again we have to update. So if we take L2, okay, the address is B1 and it is shared. Because it is read, it is shared. So which is sharing the data? P0, 0 is sharing, and it is 128, and the data is 28. Because no other processor is sharing. Now P0 alone is reading this. So that's why it is as P0, 0. This is with respect to L1 and L2. Now, what have to be done? We have to periodically, after doing this, the memory state should also be changed. So when you take the memory with the respect to so far 108 is shared by where? This here it is shared. But currently it is not shared because it is replaced with 128. So in this address 108, directory is shared by only the C1 chip, not by the C0 chip anymore. Understood? And similarly, when you take this case, C1 chip memory, same address 128, it is now shared by the processor C0, and the value is 0028. So I think this is the answer we are expecting for this operations. Here, see, when P0, 0 is performing the read operation on the address 128, first it will check the L1 cache. It's not available, it's going to be a miss. Then it will go for L2, it is a miss. Then it will go for this C1 L2, it is also a miss. Now the request will be transferred to the memory. So from the memory, the data will be fetched. So parallelly, first the data will go to L2 cache of chip 0, and then it will go to L1 cache. So we need to update both the cases. Since already it is shared, we no need to do anything. simply right, we have to replace. So we have replaced it, the block 1. Because 128 goes to the block 1, we have replaced that. And below that, 108 is no more shared in peanut. So in the memory, we are just changing 108, only C1 is sharing the data. And in case of C1, I mean, in case of here, 128 is shared by C0 alone. So this are the four changes after doing this operations. Okay. Go with another example. P0, comma 0. It is performing the write operation to the address 128. The value is 78. See, now there is no dependence. Again, this is the fresh things. So what it has to be done is it has to write the data 120, I mean, write the data 78 to the location 128. So just now we have seen the same thing, right? When you take zip, again it is chip 0. When you take chip 0, I mean, in that P0, comma 0. So we have a L1 and L2 catch miss. Similarly, if you take C1, there will be C2, sorry, yeah, C1. So there also we have a L2 catch miss. So what has to be done? The data has to be read here. So similar things, right? So the only change is what? Now it is in modified state. So that is the difference. Previously it was in shared state. Now it's going to be in modified state. So what will happen? So when you take an L1, I mean, this is C0, P0, comma 0, L1. Okay. So we have a block 1. This is in modified state and it is 128. And the data is what? 0078. Yeah, this is the data it is going to write. Similarly, in L2 also the same thing. So block 1, it is in modified state. P0 is 0 is using it. So one tag is 128 and the data is 0078. So when you move on to the memory part, the same thing. So 108 is no more shared. So it is shared only by the C1 and the data is 008. So there is no other changes. But when you take here, this is the C0 memory. When you take C1 memory, so in case of 128, it is modified by the P0 and the value is 78. So this information, this is the only change. Previously, right, it is shared, now it is modified. So that's the information we have to. So we have to be very careful. So we will go for another example. So we'll take this. So P0, comma 0, it's performing the read operation on the location 120. So what it has to do, first it will check here. It is not here, so probably right. We have a, L1 miss, L1, yeah, okay, L1 catch miss we have, and it will check L2 also. Here also, right, we have a L2 catch miss. Now, right, when you check this L2, yeah, here, right, the data is there in L2. So this has to be shared. So when it is going for sharing, what it has to be done, it is going to block 0. But when you take block 0, it is in modified state. So where the 100 is in modified state, since it is in modified, it has to be written back to the memory. Okay. So what has to be done here is, so first the step we have to do is write back the data on the location 100 to the memory. So when you're writing it, so how about the, I mean, the, like the M1 structure will be in the 100. So now we are written back. So which nobody is using that. So since nobody is using, so it is going to be what? Uncached. So this is as invalid and nobody is using it. And the data is what? 0010. Understood? Clear? This is the first step. I am going to read block 0. Block 0 is containing some modified data. That is 100. So that has to be updated to the memory. Since I'm updating from the what to say modified state, it is going for the uncached state. So now the changes will be like this. Got it? This is the first thing. Next, we need to bring the block now. So when we are bringing the block, so what are the changes? So if we take P0, 0, L1 cache, block 0, and it is read only, so it is going to be shared. The data is 120, and what is the data? It is going to be what? Okay, 0020. The same thing for L2 cache. So address is this. It is shared. Yeah, it is going to be shared by P0, 0, and externally it is shared because we have got it from L2. So it is externally shared by some other processor chip also, and it is 120. The data is 2200. This is for C0 case. And when you take this chip 1 L2 cache, so here also, right, you have the block B0, data is shared, which is sharing already according to the scenario. P3 1 is sharing. Now it is externally shared, E, because it is shared by where? It is C1, C0 also. So right, it is externally shared. It is 120 and 0020. And when you take memory, already M0 is updated. And when you go with the M1, this 120, so far it is shared by C1. Now it is shared by both C0 and C1. This data is this. So these are the changes that will happen after performing the read operation. That is P0 0, read 120. Oh, So now, right, I will go for other case. P0, 0. This is performing the write operation to the location 120 and followed by a processor like let it be here P3, 1 is performing the read operation to the address 120. So this is the sequential. One after another, it is going to get executed. So what will happen? So first, right, P0 is going to write 120. So the data is not here. So only since it is going to write, okay, P0 is going to write. So what will happen? The previous thing just now we have seen, right? So all those things. First, the block 0 has to be written back to the memory. So because we have L1, L2 catch miss, since we have L1 and L2 catch miss, the block has to be write back the 100 to memory. So when you are writing back, so according to the memory, I mean in the memory, which means in M0 100, it is uncatched, so it is invalid. So no other is using it, and the data is going to be 0018. Okay, so this is the first step. Now we need to, I mean, nothing is to be done. We are going to write the data. So when you are writing it, so I mean L1, this is C0 L1, P0, 0 is L1. So what is that? It will be because it is modified and it is 120, and the data it is going to write is 0080. This is for block 0. And when you take L2, the same thing, B0, data is, I mean, directory is modified. Yes, this is what? Right, exclusive right. So P0, 0, 120, and it is going to do this. Okay, so this what? Now, right, we have to changes. I mean, what else the changes we have to do it. So when you just go with this, I mean, here, right, this part, since 120, so this we need to change, and here also it is using that has to be changed, and here also, right, we have to perform all the changes. So what are, I mean, what are all the changes we have to do? So when you take P3, 1, so that is going to be invalid. So in P3, 1, L1 cache, P0 block, it is invalid. So the status is invalid. And when you take L2, so in case of L2, same P0. Now, right, it is modified, right? The data is modified. So since it is modified here also, right, this is invalid only. So in case of over here, it is going to be B0, yeah, L2, B0 invalid. So 120, 0020. So this is for L2. And when you take memory, now, right, 120 data is modified by C0 and the value is 80. And here, and one more, sorry, when it is invalid, with respect to this, when it is invalid, you don't need this entry also. And according to that cases they given, I think this data is invalid, no need of this. So whatever the previous data we have, only we just will retain that, but no need to mention the address tab. These are all the operations that will happen when you are writing 80 to the location 120. Now, we need to read 120. So processor P3, 1 is reading 120. So now, right, now it will check. See, when it is checking 120, it is, final operation will be like this. So when it is try to read, it will check this cache. So when it check the cache, what is cache? So P3, L1. So 120 is invalid. So then what it does, it will goes to the L2. In L2 also, right, this data is invalid. So it will check this C0L2. When we take C0L2, yes, the data is there, it's available. So what will happen? So the data will be provided here. So when the data is provided, so what else the changes? So this is the final change. This is the expected output. In case of P0, 0, L1 cache B0, it will be in the shared state 120, 00, 80. So this is L1. And when you take L2, so B0 directory will be shared. Which else is sharing? P0, 0 is already shared. Now externally it is going to be shared 120 and the data is 80. Okay, so this things is changed. Now, right here we need to update L2. So when you update L2, this part, right? So here, right, the chip 1, right? We need to go with the chip 1. So in that L2 also, we have to change. So what it has to be. So now, right, B0, the same entry. Data is shared by P3, 1, and externally it is shared, and the data is 80. And L1 is also updated to B0. State is shared. The data is 120 and the value is 0080. So moving on to the memory part, I think M1. So M1, now the 120 is directly shared by both C1 and the C0 and the value is 0080. So according to this case, so this is as a final step. This is the first operation, this is the second operation, and this is the expected output. Yes, the question will be, what will be the output after executing these operations? So this is what you have to write it. So you need to mention about L1, L2 of both the chips and M0 and M1. M0 already I wrote here. And this is the M1 condition. Clear? So like this, right, you may get some other operations and accordingly, right, you have to update the steps. Thank you, guys.